Well, good evening, everybody, and thank you for joining us for tonight's webinar on fostering proportional thinking, part, whole, and growth. This is the second of our middle school mathematical series for the summer of 2012. So we're glad to have with us Dr. Bob Horton from Clemson, and he's done presentations for us in the past, and I'm really looking forward to hearing what he's got to share with us tonight. So without further ado, I'll hand over the reins to you, Dr. Horton.
Well, thank you, Nathan, and welcome everybody. As Nathan said, this is Casio's webinar on fostering proportional thinking, part, whole, and growth. And as he said, I'm Bob Horton. I'm a professor of mathematics education at Clemson University. For the sake of audio quality, everyone will be automatically muted. If you have a question, you can type it in the question pane, and one of our facilitators will respond back privately. Or if it might benefit the entire group, may share the question and answer with everyone. If you need immediate assistance, you may raise your hand by clicking on the hand symbol in the upper left-hand corner. Proportional thinking entails far more than cross-multiplying and dividing. Several different types of proportional thinking have been defined and studied. A researcher named Susan Lehman identified 4 different types of problems involving proportional reasoning. These include part, whole, such as we find if we try to determine how much 1/3, 1/2, and 1 are if the 6 boxes of paper represent 2/3 of the number of boxes we need for a project. Growth, such as we find when we need to determine the amount of cheese, flour, butter, and water we would need to use for a different number of people if a recipe for 20 people calls for 1 cup of grated cheese, 1/2 cup of flour, 1 tablespoon of butter, and 1/3 tablespoon of water. Associated sets, such as we find when we compare the amount of pizza each person receives, when 2 pizzas are divided among 5 people, or when 3 pizzas are divided among 8 people. And well-chunked measures, such as we find when we try to determine the speed we need to travel at for the second half of a bike trip if we average 10 miles per hour on the first half of the trip and we want to average 20 miles per hour overall. And no, the answer is not 30 miles per hour. In this session, I had intended to spend the bulk of time exploring the first 2 of these, part, whole, and growth. However, while I was preparing for the webinar, though I began with a part, whole problem, I modified it so that it is now perhaps better classified under associated sets. The second problem remains one on growth. The classification is not what is important. Instead, it is the broader thinking that we hope to foster when we engage our students with proportions. My hope is to do so in a way that will provide teachers with specific strategies they can use to foster deeper thinking and better retention of important concepts. Though, as I just mentioned, the classification of problems into one of these types is not important, it is essential for teachers to appreciate the complexity that proportional thinking entails. Let's get down to business. Suppose a student's parents set up the following guidelines. For each 1 hour of study, the student would be allowed 20 minutes of phone usage, 30 minutes of television, or 40 minutes of computer time. Typically, teachers ask a closed-ended question at this point. For example, teachers might ask how much phone, television, or computer time would be allowed if the student studied 6 hours. Alternatively, teachers might ask how much studying the student would have to do if she wanted to earn 2.5 hours of computer time. The students in the class would likely be expected to set up a proportion and then cross-multiply and divide. Why, by the way, does cross-multiplying even work? We recommend a different approach. Rather than simply asking closed-ended questions, we encourage exploration. First, we encourage teachers to have students identify the variables that are suggested by the problem. Here, our independent variable, the one that the student can control, is the amount of time, measured in hours, the student spends studying. We'll name this variable X. We have 3 variables that depend on this, all of which are measured in minutes. We will label these variables Y1, Y2, and Y3 to represent the amount of time allowed for the phone, television, and the computer, respectively. How might we explore the relationships among these variables? We'll begin by creating a table of values. Let's switch over to the calculator so we can enter some values. From the main menu, choose Statistics. I've already entered study times from 1 to 6 into list 1, and then the corresponding phone times, television times, and computer times into lists 2, 3, and 4, respectively. I've already added the labels study, phone, TV, and comp to the appropriate lists. Though our focus will be on the relationship between the time studying and the other 3 variables, some discussion of the relationship between, say, the phone time and the television time might help students gain additional insights into both rate of change and proportions. For example, students could see that for an increase of 20 minutes in phone time, there is a 30-minute increase in TV time. For our purposes here, we want to notice that for every increase in 1 hour in study time, there is a corresponding change of 20 minutes, 30 minutes, and 40 minutes in phone, television, and computer time, respectively. What if the study time is 0? Certainly it seems appropriate that 0 study time would be associated with 0 phone, television, or computer time, but does the inclusion of 0 fit the pattern established by the other values? If we look closely at the data, we see that 0 does indeed fit for all lists. So let's insert 0. Next, let's explore graphs of the data. To aid us in interpreting the graphs, we'll turn the phone values in list 2 blue, the television values in list 3 red, and the computer values in list 4 magenta. To do so, highlight the list at the top of the screen, and press Shift 5 for format, and choose the desired color. We'll now set up graphs for the relationships under investigation. From the Home Statistics screen, which I can get to quickly by pressing Shift Exit or Quit, select Graph and Set. We're looking at pairs of numeric variables. Though we could create scatter plots, we'll create XY line graphs instead so that the points are connected. I've already set up all 3 graphs. Notice that list 1 is the X variable for each, and the color link is set for only Y. So here's StatGraph 1, here's StatGraph 2, and here's StatGraph 3. All of them have an X list of 1, and the Y list are lists 2, 3, and 4, and they all have a color link of only Y. After setting up the graphs and exiting the Set menu, choose Select, and turn all three graphs on and draw them. What would we want students to note from the graphs? The key aspects that suggest that the relationships between the hours studied and each of the dependent variables are proportional are, 1, that they are linear, and 2, they contain the origin. It should be obvious that the magenta is the steepest line. Why? And the blue line is the shallowest. Again, why? By tracing through the graphs with Shift F1, we can reinforce the rates of change. For each increase in 1 hour of study, there is a corresponding increase of 20 minutes. "30 minutes. And 40 minutes in phone time, television time, and computer time, respectively. Depending on the level of students, we can try the define graph option for any of the three plots to help students learn to express the relationship between the variables algebraically. For example, if I want the function for phone time, while looking at the XY line graphs, we can select F2. So let me exit, select, and redraw the graphs. And I'll select F2, type in 20x. I'm assuming we've gotten that far, and press execute. And select F6, draw. This should coincide, and does, with our plot of the relationship between study time and phone time, the blue points. This defined graph capability is quite powerful as students develop their understanding of variables and investigate rules that will help them determine how two variables are related. Alternatively, we can regress the plots to have the calculator generate the equation for us. We can then copy this into the graph and table menus. For example, while looking at the XY line graphs, we can select F1 Calc, F2 X because of the linear relationship, either F1 AX plus B or F2 A plus BX, whichever we prefer. I'll select the first one. Arrow up to StatGraph 3, the magenta one, and press execute. Once we see the equation y equals 40x plus 0, we can draw it, or we can copy it into the graph table menu. I'll copy it into Y3, since Y3 represented computer time. More importantly, we can have students interpret the equation. What does X represent? What does Y represent? What does the 40 represent? What happens when X is 0? What significance does this have? Notice that we are sowing important seeds of algebra through our study of proportions. And these questions would be a valuable use of class time. Though it may seem to some that we are jumping the gun, students as young as 5th and 6th grade can develop these ideas if we foster them carefully. Certainly students in late middle and early high school should own these concepts. From the graph and table menus, we can also ask many what-if questions. The sky's the limit here. Let's switch over to the table menu. So I'll select 7 for table. And make it so that y equals 40x is the only function selected. We can set the table however we choose, and then ask questions about this relationship. What happens if we double x? Here we can see if x goes from 1 to 2, the computer time goes from 40 to 80 minutes. But what if the x value was 10, and then it got doubled to 20? Does the computer time again get doubled? And you can see that it does. What happens if we triple it? Well, from 10 to 400, if we triple the 10 to 30, does the 400 get tripled? And we can see that it does, and we can have many explorations like that. What happens if we cut the study time in half? So if 10 hours of studying is associated with 400 minutes of computer time, what if we only study 5 hours? And notice it does get cut in half. Does this always happen, no matter what x values we start with? I just did a couple of examples here. This is also something worth an investment of time in the classroom. It's only after exploring the relationship in detail that we recommend asking closed-ended questions. We can then solve questions such as those posed at the beginning of the problem using the graph and trace and GSolve, or using the table. For example, how much computer time would the student be allowed after studying for 6 hours? Let's switch over to the graph menu. Menu and 5 for graph. Select and draw. And we'll use the trace feature to determine this. So if I studied 6 hours, it shows us that we'd have 240 minutes of computer time. How long would the student have to study to earn 2.5 hours, or 150 minutes, of computer time? Here we might use the GSolve and XCalc features. Shift F5 for the GSolve. And we can see that it would take 3 3/4 hours, or 3 hours and 45 minutes, to earn 150 minutes of computer time. At this point, we might show students how to set up a proportion as the equality of two ratios. For example, how long would the student need to study to earn 150 minutes of computer time when 1 hour study produces 40 minutes of computer time? If the time is right to teach cross multiplication, then we should emphasize the Y aspect, something we should do with all mechanical skills we teach. Cross multiplication is simply the process of multiplying both sides of an equation by both denominators. It's legal because we do it to both sides, maintaining our equality, and it's helpful because it allows us to clear the fractions as both denominators factor out as part of an expression that equals 1. Before we move on to our second type of problem, specifically growth as it relates to proportional reasoning, let me pause for a moment just to see if anybody has any questions.
Not at the moment.
Okay. Then let's move on to problems concerning growth. As with all of the categories of proportions, growth problems can range from the relatively simple to the quite complex. Though I'm calling these growth, I might just as well call them growth and shrink problems. What we are investigating is what happens when, for a given relationship, we change the size of one of the related variables. Let's begin with a relatively straightforward problem. Suppose we had a picture that was rectangular in shape, with a width of 6 centimeters and a height of 8 centimeters. But we needed to reduce it or enlarge it to fit a different frame. What would happen to the height if we made the width, instead of 6, we had to make it 3 centimeters? What if we made the width 9 centimeters? The major concern here is whether students will look at the transformation as additive or multiplicative. For example, as the width changes from 6 centimeters to 3 centimeters, will students think that the height changes from 8 centimeters to 5 centimeters or from 8 centimeters to 4 centimeters? Similarly, when the width changes from 6 centimeters to 9 centimeters, will students think the height changes from 8 centimeters to 11 centimeters or from 8 centimeters to 12 centimeters. First, by drawing and evaluating figures, and I strongly recommend graph paper for doing this, students should discover the correct solution to this. From here, the teacher can lead students to understand the importance of preserving the ratio of width to height. We do not need to preserve the distance between the width and the height. Thus, if we multiply the width by 1/2, which of course is equivalent to dividing by 2, a lesson for a different day, then we must multiply the height by 1/2, or divide it by 2. Similarly, if we multiply the width by 1.5, then we need to multiply the height by 1.5 to preserve the appearance. In other words, the relationship from this perspective is multiplicative, not additive. Students should also be encouraged to compare the ratios of the widths to the heights. There are, of course, many ways to do this. In the Run Matrix menu, so I'll go back to the calculator and go to the Run Matrix menu. One way is to enter the ratios as fractions and see if they reduce to the same values. For example, does 6 to 8 reduce to the same value that 9 to 11 reduces to? Didn't work there. Or to the same value that 9 to 12 reduces to? And that did reduce to the same ratio. Another way of checking this is to introduce the idea of truth tables, albeit somewhat subtly. A true statement receives a value of 1, while a false statement receives a value of 0. Here we can check whether the ratio of 6 to 8 is equal to the ratio of 9 to 11. 6 to 8 equal the ratio of 9 to 11. We get a 0, which indicates no, it does not, or to the ratio of 9 to 12. So let's try 6 to 8. Does that equal the ratio, does that equal the ratio of 9 to 12? And here we get a 1, which indicates a true statement. So this is the one we want. We'll now look at the idea of growth problems from a different perspective, in a different context. Let's consider a situation in which a teacher has given a quiz. We won't concern ourselves with how many students made each score, but let's assume the scores were 0, 10, 20, 30, 40, 50, 60, 70, and 80. In other words, if we assume these represent points out of 100, or percentages, the grades were not very good. The teacher decides to modify the grades and is considering two plans. For Plan A, the teacher will add 20 points to each student's grade. For Plan B, the teacher will add 25% of the current grade to each student's grade. Let's explore these two plans numerically and graphically, and then determine if either, or perhaps both, suggest a proportion. We'll return to the Statistics menu. I've already entered the scores into list 6, and I've called them the original scores. Note that without knowing how many students obtained each of these scores, we cannot determine the mean, the median, or other statistical values that might be of interest. Nevertheless, we can still see what happens with each of the two plans. In list 7, we'll transform the data by adding 20 points to each of the values in list 6. We highlight list 7 at the top and press Shift 1 for list, 6 to identify list 6, the addition symbol, and 20. Pressing execute will create our new list for us. We'll turn list 7 blue as we did earlier. And we'll label the list as Plan A. We'll do something similar now for Plan B. We could take the values in list 6 and add to each 25% of its value. Alternatively, we could take 125% of each of the values by multiplying by 1.25. We'll choose the latter. Highlight list 8 at the top and press Shift 1 for list, 6 to identify list 6, the multiplication symbol, and 1.25. Pressing execute will generate the list for us. Let's turn list 8 red and label the list as Plan B. Shift format and 3 for red, and I'll call this Plan B. As a side note, this context can be used to explore transformations. Plan A is a translation, and Plan B is a dilation, something we could show by exploring the statistics and different graphs such as box plots. However, that's not our purpose in this webinar. Let's look at graphs of the two plans using the original scores as our independent variable and our modified scores as our dependent variable. As before, XY line plots are appropriate. What do we expect to see? For many, they will think that Plan A is linear because of the constant change in the dependent variable. For every increase in 10 points in the original score, there's a corresponding increase of 10 points in the modified score. However, many people, especially before they've studied the data and the graph, often don't know what to expect for Plan B, as they're not sure what effect the multiplication will have on the graph. So let's take a look. From the statistics home screen, which is where we are, select F1 graph and F6 set. We'll use the setups for StatGraph 1 and StatGraph 2, but change the X list to list 6 for both. And the Y list for the first one to list 7. And for the second one, list 6 again for the X variable. And list 8 for the Y variable. And I still have the color link set on only Y. We'll exit. We'll use select. And this time we want StatGraph 1 on, StatGraph 2 on, but StatGraph 3 should be off. And we'll draw the graphs. So what do we see? As expected, the graph for Plan A, the blue one, is indeed linear. Did you anticipate that the graph for Plan B, the red one, is also linear? You may want to change the scales. I have my X scale set at 10 and my Y scale set at 20. Let's first look at Plan A, the blue line. It has a y-intercept of 20. Notice when X is 0, 0 on the original corresponds to 20 on the modified score. The next point shows that a score of 10 corresponds to a modified score of 30. So a 10 on the original corresponds to a modified score of 30. The slope, therefore, is 1. For every 10-point increase in the original, here from 0 to 10, there's a corresponding increase of 10 points in the modified, here from 20 to 30. Though notice I do have different scales going on in my graph here. This rate of change remains constant throughout. It is linear, but it is not proportional. We'll talk about that more in a few minutes. What about Plan B, the red line? The graph has a y-intercept of 0. 0 on the original corresponds to 0 on the modified. A score of 10 on the original corresponds to a modified score of 12.5. A rate of change of 12.5 points to 10 points. This gives us a chance, if we want it, to work with complex fractions. In simplified form, this is 5 to 4, something we can verify from the Run Matrix menu. So I'll do that. Let's go to the menu, Run Matrix, and let me delete what's here. And I'll introduce a mixed number of 12 and 1/2 to 10. And we can see it reduces to 5 to 4. Students might instead skip 2 points. Let me go back to the graph, menu statistics, and I'll go to graph and select and redraw them. Rather than going to consecutive points, I could have chosen the rate of change between 2 different points if I wanted to. Okay, we were tracing. So from 0 to 0, we went up to 10, 12.5. I could have gone up to 20, 25 to make that rate of change a little bit easier to see. But notice as I go from 10, 12.5, my rate of change remains the same. My increase of 10 points on the original corresponds to another increase of 12.5 points on the modified. In fact, a good exercise for students is to pick different pairs of points to ensure that the rate of change between any 2 points is constant. Here, the rate of change is 5 points on the modified Plan B scale for every 4 points on the original scale. Therefore, Plan B is, like Plan A, linear. In addition, Plan B is proportional. Graphically, we can tell this because it is linear and because it goes through the origin. Let's now look at it a little differently. From the graphs, I'll press Exit to return to the list. And let me get back to the list where I was. We'll now check the ratio of the modified scores to the original scores using division to make that comparison of ratios. In List 9, let's look at the ratio of Plan A to the original scores. When we highlight List 9 and try to find the ratio of List 7 to List 6, List 7 divided by List 6, we get a math error. Similarly, if we try to find the ratio of List 8 to List 6, we also get a math error. This is because we are unable to divide by 0. So before we investigate the ratios, let's see what happens when we remove the first value from each of the 3 lists. So I'll press Exit and Exit here, and I'm going to go into the first value in each of the lists, and I'm going to simply delete the first value. So the 0 is gone from the original, and the corresponding 20 is gone from Plan A, and the corresponding 0 is gone from Plan B. We'll now put the ratio of Plan A scores to the originals in List 9. So List 7 divided by List 6. That's in List 9. And in List 10, I'll put the ratio of the Plan B scores. So List 8 divided by List 6. Notice we're able to do it now because we're no longer dividing by 0. The differing values in List 9, notice they're getting smaller, but they are different is the key point here. These differences tell us that Plan A is not a proportional plan. For example, those who scored only 10 points on the original have their scores tripled from 10 to 30 ratio of 3, while those who scored 40 on the original have their score multiplied only by 1.5, from 40 to 60. Is this fair? Maybe yes, maybe no. What's important is to recognize that though each score was increased by 20 points, those who scored poorly on the original receive a greater boost relative to their original score. On the other hand, note that list 10 contains only the value 1.25. In other words, everyone, no matter how they did on the original, has the original score increased by 25%. This tells us that Plan B is a proportional plan. Though the number of points that are added varies, everyone receives the same relative increase. That is, all scores are increased by the same percentage. Whether Plan A or Plan B is fairer is open to discussion. Perhaps if there are a couple of poorly worded questions on the test, then each person's score should be boosted by 20 points, suggesting Plan A is fair. Alternatively, if the questions were difficult but fair, perhaps those who did quite poorly on the original didn't study, and they don't deserve to have their scores boosted by as many points as those who did better. This, too, is something worth discussing in math class. In any case, we want teachers and students to understand that Plan A is not a proportional plan, while Plan B is. Another way to see that Plan B is proportional is to note relative changes. To be proportional, the ratio between corresponding scores must remain constant. For example, if one score is double another on the original, it should be double after the plan is implemented. For example, under Plan B, original scores of 20 and 40 become 25 and 50, respectively, so that the second score is still twice the first. Similarly, consider original scores of 20 and 60. So 20 was a 25, 20 became a 25. If that original score was tripled, somebody who got a 60, their modified score is a 75, so that the second score remains triple the original, from 25 to 75. Investigating the ratios in this manner can help shed light on what it really means when we have a proportional relationship. So what is a proportion? Under what conditions do we have a proportional relationship? Too often we ignore the assumptions that we make when we consider proportional relationships. Let me return to the PowerPoint here. For example, if we know that a box of our favorite cereal costs $3.50, we might determine that 2 boxes cost $7. Do we have justification for such a conclusion? In typical, though not all, situations, we would be correct in making this determination. Our assumption of a proportional relationship is reasonable. Note, however, that we have a single data point, one box, $3.50, that we have used to compute really a mathematical model, even though there are an infinite number of mathematical models that we could have computed instead. To explore this just a little further, consider a similar situation. Suppose that $3.50 box of cereal, contains 14 ounces. As just mentioned, we would probably expect 2 boxes of cereal, which would give us 28 ounces, to cost $7. However, what if there's a giant box of cereal that contains 28 ounces? Would we expect this box to cost $7? Most people would think that we would be better off if we purchased the bigger container. Why? We intuitively think we do not have a proportional relationship, that the unit cost, the cost per ounce, of the larger box should be less than the unit cost of the smaller box. So let's be specific. What assumptions are we making when we set up a proportion based on a single point? First, we assume we have a linear relationship between the two variables under consideration. In other words, for every set increase in one variable, there is a consistent increase in the other, a constant slope. Second, we assume that our mathematical model goes through the origin. In other words, 0 of one quantity corresponds to 0 of the other quantity. For our cereal example, when we decide that 2 boxes should cost $7, or 3 would cost $10.50 for that matter, we are assuming first that each box costs the same amount, and second, that 0 boxes cost $0. Though this may seem obvious here, consider again the modification to our example with the 14-ounce box and the huge 28-ounce box. We may indeed have a linear relationship. That is, each additional ounce of cereal may cost the same additional amount. However, with different sized containers, the pricing model does not contain the origin. Even though we wouldn't pay anything if we didn't buy any cereal, the pricing model probably contains fixed costs, such as the cost of packaging and shipping. The model does not contain 0. In other words, though each additional ounce may cost the same amount, that amount is not $3.50 divided by 14 ounces, which would suggest 25 cents per ounce. The pricing model might be something like y equals 42 cents plus 22 cents times x, where x represents the number of ounces and y represents the cost. The relationship is linear, as each additional ounce costs us an additional 22 cents. But it is not proportional. There are fixed costs of 42 cents built into the pricing structure. Again, it is not proportional. Getting twice the number of ounces does not cost us twice as much. Another strategy for determining a proportional relationship is to consider the ratio between the two variables. For a proportional relationship, the ratio must be the same for every ordered pair. Algebraically, we can express the relationship as y over x equals some constant k. Note that we can transform this and write it in the form y equals kx. This suggests a linear relationship with a y-intercept of 0. In other words, these two different ways of viewing proportional relationships are equivalent. Before we wrap things up, let's revisit the 4 problems we looked at initially. Our initial part-whole problem requires people to rethink what a unit is. While unit does refer to one whole, in this problem, one whole is a collection of boxes. Because 2/3 of our whole contains 6 boxes, 1/3 must contain 3 boxes. Consequently, 3/3, or one whole, must contain 9 boxes. This also suggests that 1/2 consists of 4.5 boxes. These can be some pretty complicated ideas for students unless we give them appropriate experiences to help them make sense of them. Our growth problem that we presented early on is one that helps us realize that we have to preserve ratios in proportional situations such as this. We note that the ratio of 4 people to 20 people is 1 to 5. Therefore, we need a ratio of 1 to 5 for each of the ingredients in the recipe if we're making it for 4 people. So for 4 people, we need 1/5 of a cup of grated cheese, 1/10 a cup of flour, 1/5 a tablespoon of butter, and 1/15 a tablespoon of water. These amounts can be pretty difficult to measure. We'll leave the remainder of the solution to you. For our associated sets problem, we're looking at a comparison of ratios. If 2 pizzas serve 5 people, then each person should receive 2/5 of a pizza. Students should be challenged to determine this on their own and may see that cutting each pizza into 5 equal pieces will guide them to the solution. If 3 pizzas serve 8 people, each person should receive 3/8 of a pizza. There are many ways to compare these to conclude that each person gets a little more when 2 pizzas are shared among 5 people. Finally, our problem on well-chunked measures is one that people often don't recognize as a proportional situation, but it is a little tricky. We cannot average the rates. Even though we would have traveled the same distance at the 2 rates, 10 miles per hour for the first half of our trip, and what we are seeking for the second half, we do not travel at these rates for the same amount of time. In fact, by traveling at half of the desired average rate, we would have already used up all of the allotted time for the entire trip. Consequently, if you average 10 miles per hour for the first half of the trip, it is impossible to average 20 miles per hour for the entire trip. For the biking enthusiasts among you, if it seems like the majority of your time is spent going uphill, you're right. Even though half of your travels are uphill and half are downhill, at least in terms of distance, because you go more slowly uphill, you spend more time going uphill than you do downhill. Let me pause once more to see if anyone has any questions before we really wrap things up for the night.
No questions so far. Thank you.
Okay. We hope you've enjoyed this webinar and that it has caused you to think, aroused more curiosity, and helped you realize that with proportions, there is typically more than what meets the eye. We also hope you can see what a powerful tool the PRISM can be for fostering proportional thinking. We encourage you to read and then engage your students in the many investigations involving proportional reasoning contained in the book Fostering Mathematical Thinking in the Middle Grades, as proportional thinking is critical to understanding higher level mathematics. Despite its importance, however, it is far more complex and deserves far more attention than it is often given in the classroom. We also encourage you to attend other webinars sponsored by Casio as we all strive to make the mathematics classroom relevant, interesting, thought-provoking, and about sense-making. For more information, please visit www.casioeducation.com, www.casioeducation.com/prism, and www.casioeducation.com/support/educators/webinars. Thank you for your participation, and good night.
Thank you very much, Dr. Horton, and thank you to all of those who joined us this evening. Hope you have a good evening.